is actually defining a recursive structure, a recursive data structure. How do I end the recursion? Well, I use nil. So if I don't want to provide like another node, then I would use nil and then count that. The end that signifies the end of the linked list. Okay, so then so this is my data type, and then we can create like some example linked lists. So for example, list 1, we might have it be a 3-element list of strings. So we could say like node foo, and then so now we're at this list part, right? So we have the node constructor, but now we need to get the list. So we'd use the node constructor again to create another node, a bar, and then we have one more, which is Baz, and then we end it with nil. So that's kind of like the end of the linked list. So this, you can think of it similarly to a linked list. That looks maybe something like this. Okay, and then if I asked, if I want to know what the type of list 1 is, Haskell can tell me. So first of all, what we see when we look at list 1 is the first thing is we're using the node constructor. So this tells us that it's a list type, okay, because node is defined to be a list value constructor. And then the only thing that's missing is what the type parameter is. Okay, it's a list of what? And so in this case, it's a list of string. And so if we asked Haskell to tell us what the type is, it'd tell us that this is a list of char, which is a list of string. Okay. Any questions about this? Okay. So then, actually, I'm going to erase this unless anyone. Is that okay? Will anyone complain if I delete this for now? Or just delete it? Okay. All right, so going back, what we also, I kind of showed at the very end is that just like with anything else in Haskell, we can use pattern matching. To define functions, or we really have to use pattern matching to define functions over our user-defined data types. And so one useful function for a list, for example, is the isEmpty. Oh my gosh, okay. Okay, there we go. Is the isEmpty function. Okay, so basically, given a list, I want to be able to say whether or not that list is empty or not, right? Return true or false. If the list is empty, it's going to return true. If it's not empty, it's going to return false. So it's very simple. So the type of isEmpty, it takes a list, and it can be a list of any type, doesn't matter. And then it's going to return a bool. And then we would define this using patterns. So the most obvious case here would be if I give it an empty list, okay, where an empty list is represented by just the nil value constructor. And so in this case, I want to return true. If you give me an empty list, a nil node or whatever, then that's empty. And then using pattern matching, it's actually quite easy. We don't care what else if we get something else other than nil, then we know it's not empty. Because the only other thing that can go here is basically a node constructor. Okay, so that one's pretty simple. And then the other one we talked about is length. So we'll call this list length. And in this case, again, list length is going to take a list, and then it's going to return the number of nodes in the list. So to do that, we'll just assume that what gets returned is an int value. We're not creating like ginormous linked lists. So then, again, to define list length, we need to use patterns over our data type. And that always works over the value constructors. So, and then in addition, because it's a linked list, to define a function that computes the length of a linked list, we really have to like traverse through the list and count up all the elements as we go. So because Haskell doesn't have any notion of iteration, the only way we can iterate through a list, doesn't have looping, or a looping construct. The only way to do this, the most natural way to do this, is just to use recursion. Okay, so when we think about recursion, there's always a base case and a recursive case. So we'll start with the base case, which is that if the list is empty, then the length of the empty list is 0. So again, just like with is empty, I can match on the nil value constructor, which suggests that the list is empty. And so in this case, the length of the empty list, like I said, is 0. And then we have the recursive step. And here is where it gets maybe a little bit more interesting. So just like with the book example, in the non-empty case, I'm matching on the value constructor. And I have to wrap that, when I do pattern matching, in parentheses. So I'm going to have to put parentheses. I'm matching on the other value constructor, which is node. In this particular case, I don't care what the value is in the node. I don't need that to calculate the length. I just need to know basically that it's a node, that's not nil. But I also need to then calculate the rest of the length. And so I need to keep track of basically like the tail of the list. And in terms of recursion, the basic idea is if I'm sitting at a node, that counts as one element in the length. And then to figure out the entire length of that portion of the list, it's that node plus however long the tail is. So then I need to calculate the length of the tail. And that's the entire function. Are there any questions about that? About this stuff?
Instead of using pattern matching, you could just as easily use guards, right?
I could use a guard. Yeah, I could use a guard. It'd be a little awkward, but I could say something like list length of L. Okay. If L is equal to nil, then it's 0. Otherwise, I still need to, so here I need to somehow get the tail. I'm going to still have to get the tail. So I still need to use like some form of pattern matching here. Does that make sense? because I want this to be 1 plus the list length of the tail. Okay, so anyway, I would argue this is better. Here, I believe you could still match to say that it's equal to that, or in parentheses. But really, this is bad. Like, you shouldn't do it this way. In this case, it's much better to just, it's more straightforward to do it, just using patterns in this case. What? Okay. Sorry, that's my background. Okay, so any other questions? About this? Okay, so I'm going to move on. So one thing I just want to say real quick is this is basically kind of like a very minimal starting point for homework 10. So your job in homework 10 is to define a very similar linked list structure, but you're going to implement all the functions sort of necessary for implementing a multi-set or a bag in terms of a linked list. And so just for clarification, so a set contains a collection of unique unordered values, right? So the basic idea is in a set, there's no duplicates. So you only have one of things. So for example, if I have a set, I don't know. Okay, if I have a set with the elements A, B, and C, okay, so I can't have a set where A occurs twice in it, for example, because it only supports unique values. And order doesn't matter. So for example, this set is equivalent to this set, for example, because order doesn't matter. Okay, so this is a set. So it's an unordered collection of unique values. So a multi-set, which is more commonly called a bag, is like a set where order doesn't matter, but you can have duplicates, and you need to keep track of the duplicates. So for example, this is true in a bag, but this is not the same. And why? Why aren't these the same?
One of them's got 2 A's.
Exactly. This has 1 A, this has 2 A's. So duplicates matter. Order doesn't matter, but duplicates matter. So the way that you're going to represent a bag is as a linked list. So in this case, the linked list would have the value B, as well as the number of occurrences of B in the bag. So here there's just one occurrence. Then we would have A, let's say, and there's 2 occurrences, and then we have C, and there's 1 occurrence. So the basic idea is you're taking this definition of a list, you're going to call it a bag instead of a list, and you're going to add a count field. So this is going to have an int, basically, which represents the count. And then your job is to implement a number of operations over the bag. And so one of the things, as you're doing this, one of the things I'd like to say, or just to point out, is that Haskell is a more declarative programming language than many other imperative languages, since it's got this functional nature to it. So as you're defining the functions, you should really be kind of meta thinking about what am I saying in this definition? Because the nature of Haskell when it comes to these kinds of things is that you're getting very close to what you would almost think of as like the mathematical definition of the operations. So there's a few things that I'm asking you to do in the homework assignment. So for example, to write a function which checks if one bag is a sub bag of another bag. And I tell you what that means when what that means to be a sub bag as opposed to a subset. However, when you actually define the function in Haskell, because it's very concise and just the nature of Haskell with patterns and so on, hopefully you can see, and you have to kind of reflect on it as you're doing it. You have to be thinking about this, that what you end up with is something very close to how you would actually define this mathematically, by cases. And so as you're going through stuff, you should really try to do that, is to think of it not so much as a programming language, but almost like a specification language. You're defining what it means to be a sub-bag, or to combine two bags together, or whatever the function is. It's more of a specification language, and then it just so happens that it's also a way to execute these operations. Okay, so I'm going to stop. And I'm going to move on to give another example of user-defined types, which is for binary trees. Sorry. There we go. Okay, so what I'm going to do is just walk you kind of through an implementation for standard binary search trees. Actually, I should clarify this. Sure, why my pen is unhappy. So the first thing that we need to do is to define the data type. So here we'll define, we'll call it tree, even though it's really a BST or binary search tree. Again, like for a list, each of our nodes in the binary search tree is going to have a value. And we'll have two different value constructors. So we have nodes, and then we'll have the empty tree, nil. Okay, and a node holds the value, and the value's type is A. And then if you think about a node in a binary search tree, instead of having like a next pointer, it has a left and a right pointer. Okay, so if I'm defining a tree data type, what do I need to put here? Well, I need to put the left and the right pointer. There's no pointer, so what is the value of the thing I'm putting in those slots? Somebody tell me.
That would be nil, right?
In this, so here, let's say that's nil, right? The right one is nil, but then let's say here, actually it's got another child, right?
Be a tree.
It'd be two trees. In this case, yes. So the left, this is the left. So really what goes here to the left of the left child or whatever is really a left subtree. And so we have a recursive data structure again, but where we actually have like double recursion because we have the left subtree and then we have the right subtree. And what this is saying is that a tree node has a value of type A, and then it has a left subtree of type A and a right subtree of type A. Okay, or we have an empty tree. And then you would do the kind of the normal deriving, show and EQ. Okay, so if I want to create a tree, then let's say T1. So I can create a tree node, and then, so let's say I'll call that B, or the value is B, and then it'll have a left subtree. So let's say that's another node, A, and then that doesn't have any children. I'm kind of out of room. So then I would have another right child. Actually, in this case, I'll just say the right child is nil. So in this case, T1 is this tree where the root is B, the right is empty, and the left is another node with the value A. And then those are also empty. Any questions about that? Just about how the structure works? If I wanted to add more stuff here, you know, I'd just put more nodes on the right-hand side, basically. Oh, actually, I'll get rid of this. Okay. So, so I'm just going to go through, and it'd be great if people could kind of help me here to create some of the normal like functions you might have if you're defining a binary search tree class. Let's say some of the methods you'd have. So the first one we might do is another like is the tree empty. Which is probably unnecessary, but let's say we'll do that anyway. So isEmpty is going to have a type, and it's going to again have two cases. So the first case is if I have an empty tree, which is represented by the nil value constructor, then what should isEmpty return?
True.
Good. And then for any other case, it's got to be false. So if it's not nil, then it's also not empty. What's the type of isEmpty?
Treatable.
So it takes a tree, type A, and it returns true or false. So that's tree abatable. Good. Okay. So let's say we wanted to do a function to calculate the size of the tree. Okay, so the size, which is kind of like the length. But for a tree, the size of the tree are the number of nodes in the tree. Okay. So the type, well, first of all, it takes a tree of type A, and then it's going to return a number or an int. So we'll just say, in this case, int. So it takes a tree, it's going to return the size as an int. Again, we're going to have to implement this using recursion because there's no way to like iterate through. And in fact, that's really the normal way you would implement the size function over a binary search tree anyway. You do a traversal through the tree. And you're going to usually do, left deep, left to right traversal. So the base case would be empty tree. And in that case, the size is just going to be 0. So it's just like length, basically. And then I have the non-empty case. So now I have to do pattern matching. The only other thing besides a nil value constructor is a node value constructor. So here I'm going to match on node. Again, just like with length, I don't really care. I'm not going to use the value, so I don't do anything with it. And then I need to match on the left and the right subtree. So in this example, or in this case, I'm going to call the left subtree L and the right subtree R. And so the size of a subtree is basically 1 for the root plus the size of the left subtree plus the size of the right subtree. So the result is 1 plus the size of L plus the size of R. Any questions about that? Okay. So another useful metric for a tree is a tree's height. Okay, so we're going to do height. Whoop. Height function. So again, height takes a tree and it's going to return the height as an integer. So I always like to define height such that if I have an empty tree, it has a height of 0. Some people define it as 1, but it just works out better, I think, if you treat that as 0. And then I have the next case where I have, again, a node. I don't care what the value is. I don't need that to calculate the height. But I do have the left and the right subtree. Okay, so the way the height is defined is basically if I'm sitting at a node, I need to calculate the height of the left subtree. And then I need to calculate the height of the right subtree, and whichever one is greater is, I add 1 to it for the root of the subtree, and that gives me the height of that subtree. Okay, so it's 1 for the root, okay, plus I'm going to take the max of the height of the left and the right. So max is a Haskell function, and it takes 2 arguments. So the first argument is going to be the height of the left subtree, and the second argument is the height of the right subtree. And that's the whole function. Okay. So any questions so far? Okay. So now we'll get into the more kind of useful parts of a tree. So one thing is, it'd be nice to be able, if we're going to do a binary search tree, it'd be nice to have an insert function so that given a tree, I can insert a value into it and it'll put it in the right spot. Okay, so we'll start with insert. We'll leave the type here for a second. So again, the way insert works is you kind of navigate down to where the value should be, and then you put a node with that value at that spot. So the first case would be, let's say I'm trying to insert the value x into an empty tree. Okay, well that means now since the tree is empty, I need to put a node. I just need to create a node and put x in there. So x becomes a new node, or I create a new node for x, and then the left and the right subtrees are empty. Okay, so far so good. So now I have the case where the node that I'm at, as I'm kind of navigating down the tree, it's not empty. Okay, so I'm trying to insert X. Now I'm trying to insert it into a node. And let's say the value of the node is Y, and it has a left and a right subtree. Okay. So in this case, if X happens to be less than Y, then what I need to do is basically I need to insert X into the left subtree of this node Y. So I'm going to keep node Y around because as I'm kind of navigating down the tree, I'm also building it back up. I'm building a tree back up. In some sense, you know, all of these functions are going to do that. So insert isn't modifying the existing tree. We can't do that. It takes a tree, it creates a new tree that's the same as the old one, but modified for whatever it is we're trying to do. In this case, it takes the old tree and it basically copies that into a new tree with the X value inserted. Okay, so that's why we have to keep node Y around. We're actually building up that node again as the output. Okay, so then in this particular case, I'm doing a recursive call. I want to insert X into the left subtree. So I'm going to call insert, passing in X, and I'm going to insert it into the left subtree. And I don't touch the right subtree at all, so that just stays the same. Okay, and then I have the case where X is greater than or equal to Y. So I'll just say here, otherwise, I'm going to keep Y again. I keep L intact because I'm going to go, I need to insert into the right subtree. And so here I call insert again, but on the right subtree. Okay, any questions about that? What's the type of insert? What does the insert take as an argument?
A tree. Tree.
A tree. Okay, good. So it takes a tree. And what does it return?
Is it a new tree?
A new tree. And that tree is defined over the same type as the input tree. Okay, so however, there is a type constraint. And that's true of a binary search tree. In order for me to insert a value like X into a binary search tree, I have to be able to compare X to other values in the tree. And so here I'm using less than to do that comparison. So that means that the type of values I'm sticking into the tree have to support the less than operator, which the types that support the less than operator are types that are members of the ordered class or ORD. And so in this particular case, there's a type constraint, which is that the A types have to be ordered. I can have a tree and do the other three operations. Doesn't matter if they're ordered or not. I can still do the operations. It's like independent of whether the stuff is ordered. But for insert and all the other operations we're going to do, it has to be ordered, right? The values have to be ordered. That's just the nature of a binary search tree. There is actually a way to specify that in the type itself, but we don't really, why over-constrain things? We don't need to over-constrain it.
Also, it takes the value it's inserting as a parameter.
Oh, good. Yes. Thank you. Jumped the gun. Of course. There we go. Okay. Any questions about insert? Again, if we kind of look at insert, it's like, it looks way more like some kind of a mathematical function than what we would do in C or C++ or Java or something, right? We're just defining it like by cases, and it's very specific. It's really easy to see what's going on, I would say. Okay, so the next one we're going to implement is find. And so we'll hold off on the type for a second. So the basic idea of find is it takes a value and then returns true or false depending on if that value is in the tree or not. So we're asking, is this value in the tree? So if I call find, again, I have to navigate the tree in order to do that check, but I'm really just navigating down a path of the tree, right? Because I take advantage of the binary search tree constraint. So if I'm trying to find a value, and I don't even care what the value is, if I'm trying to find some value in an empty tree, then I'm not going to find it. Okay, so in this particular case, I'm going to not return that. I'm going to return false. If I navigated down a path and I got to an empty node or an empty tree, I'm not going to find the value. Okay, so then I have the recursive step. So let's say I'm trying to find a value x, and I have a non-empty tree, and I'm sitting at a non-empty tree rooted at this node y, and then it has a left and a right subtree. So then, just like with insert, I'm going to take advantage of the binary search tree constraint. So the first thing is if x and y are the same, okay, if x and y are equal, then I found a match and I can stop searching. So here I would just return true. I found a match. Okay, if x, though, is less than y, then I didn't find a match yet, but I need to keep searching. And in this case, I need to keep searching in the left subtree. And so I don't need to build back up the tree. So I'm just going to do a very simple recursive call, which is I want to look for x in the left subtree. Okay, and then the otherwise case, I want to look in the right subtree. I'm trying to find x in the right subtree. So again, if we go back to the type, because I'm doing these comparisons, I have to implement ORD again. So the type has to be ordered. And find takes the value, takes a list over that value, and returns a bool. Hold on just a sec, sorry. Okay. Any questions about that?
It takes a tree, right?
Oh, thanks. Okay, good. All right, so the last one, so here's our binary search tree so far. And really, I would argue the first two, maybe this one is empty, is kind of useless. So far, we're basically at this point. We've implemented these 4 operators. Okay, so the last one is the hardest one, which is delete. We'll do the type in a sec. So in this case, so basically we give a value and we want to delete that value from the tree. Okay, so if the value is not in the tree, there's nothing to do. So the first case is going to be I'm trying to delete a value from an empty tree. And so in this case, I just return the empty tree. Again, just like with insert, when we delete, we take in a tree and then we produce a tree as output. And so as we implement delete, we have to build back up the correct tree. Okay, so then we have the non-empty case. So we're trying to delete a value x from a node or from a subtree. And so that subtree is rooted at y, and it has a left and a right subtree. So then, again, just like with binary search, or with find, sorry, there's 3 different cases. So the first case is if x is less than y, then I need to delete. So first of all, the node that I'm sitting at isn't the one I want to delete. I need to go into the left subtree and do the deletion. So again, in this particular case, I'm going to keep node y, then I'm going to delete x from L, and I keep the right subtree because I don't touch the right subtree. Let me clean that up. Sorry. I'm going to delete x from the left subtree, and I keep R intact. Okay, I'm going to search basically for x in the left subtree. Then I have the case where x is greater than y, and again, I'm going to keep y, I keep L, and in this case, I want to delete x from the right subtree. Okay. And then I have the case where I actually found the node that I want to delete. And so in this case, I can't delete, I'm not going to delete it right now. I'm going to instead use a helper function. So I'm going to call my helper function delete prime. And all I'm going to pass it in is the node that I want to delete at this point. So here, since x and y are the same, I want to delete, I'll just call it y, or I'll call it x. I'm going to delete x with a left and a right child. I could have just as easily put y there. Doesn't matter, because they're the same. Okay, so I'm going to use this helper function. So if you you have to go back to 223. So let's say, give some space. So I've navigated down the tree. Now I have a node D. That's the one I want to delete. Okay. Or in our case, this is X. This is the X node. And there's a few different cases with respect to the deletion of this node D or the node X. So the first case is if the node only has one child. Okay, if it only has one child, that's like a super simple case. All I do is delete D, and then in D's place, I put the child. Okay, so we'll start with that. And here we're going to use a where clause to define our delete prime function. Okay, so there's basically 2 cases. Well, there's 3 cases. There's when D doesn't have any children, or D has a left child, or D has a right child. But it turns out that we can collapse those really into just 2 cases. One where it doesn't have a left child, and one where it doesn't have a right child. Okay, so we'll start with the first case where it doesn't have we'll start with where it doesn't have a left child, which is a little different than nodes, but it's fine. We don't even care what the value is, we're deleting it. The left child is nil, the right child may or may not be nil, and so the result of doing this is just returning the right child. Okay, and then there's the case where the node has a left but not a right, and here we just return the left child. Okay, so those are the two kind of easy cases. So the third case is where the node has both a left and a right child. It's got a left and a right. So we'll just draw it this way as kind of a more general case. We'll call this S here. So the basic idea in the case where there's two children is we can't just delete D and replace it with one of its children. That requires a lot of work and probably like rotations and changing the tree. So instead what we do is we find the in-order successor. Okay, which means we go right and then we go left as far as we can. So in this case, S is the in-order successor. So then we're going to take the in-order successor, the value, and we're going to copy it into D. So the second step is a copy. We copy S into D. And then the third step is we're going to delete S. And what we know, based on the fact that S is an in-order successor, so the way to find the in-order successor is we go right, then we go left as far as we can go. So what we know about S is it does not have a left, because if it had a left, we could keep going, but it may or may not have a right. And so deleting S is one of these simple cases again. So we basically did a copy in order to go to a simpler case. Hopefully that's a refresher. Everybody should know this. Okay, so if I come back to my function, so I have the case now, where I'm trying to delete a node. Here it's X again, and it's got a left and a right node. So in this particular case, what I'm going to do, the way I'm going to define this, I'm going to use a let expression. And I don't really have to, but it's just kind of a nice example of it. So I'm going to define a helper function that'll find the in-order successor for me. Okay, and I'm going to say that S is that in-order successor. So here I say let S equal the in-order successor of R. So in other words, I go right, and then the in-order successor is just going to go left as far as it can. Okay, and then once I found the in-order successor, I'm going to do the copy. Okay, so which means I'm going to return a node that has Y instead of, it has S in place of X, so that's the copy. The left child, or the left subtree stays the same, but from the right one, I have to delete S from it. And then whatever I get back, that's going to be the subtree, the right side of the subtree without the in-order successor. Okay, and then the in-order successor is actually really easy. So if I'm sitting at a node with a value, we'll call it S here, that does not have a left, then I just return the value. Okay. Otherwise,
would this need to be in a where block or no?
This is all in one where block.
But like the definition of in-order successor can just be on its own?
No, it's in the where block.
Oh, okay. Okay, so you can define multiple functions in a where block.
Yeah, you can have many bindings, lots of different helper functions. You can do whatever you want in there.
Okay. So
in this particular case, so an in-order successor has two cases. One, where basically I can't go left any farther. That's the first case. The second case is I can go left, and so then I need, wow, I'm running out of space. I want to keep going left. So I'm going to look for the in-order successor of the left subtree. So this is just navigating down the path, going left as far as I can go. Okay, and that's the whole thing. So if we look at delete, again, delete has this ordering constraint because of the comparisons. So this has a type constraint on A. And then in this particular case, again, we take the value we want to delete, we take a tree, and then we return another tree. Let me shrink that, sorry. And my pen's dying. It takes the value, it takes a tree, and then it returns a new tree. So if we don't include the size function, which is, or sorry, if we don't won't let me go that small. If we don't include the isEmpty function, so basically all of the operations that you would consider for a binary search tree, the normal operations, it's in Haskell, it's really quite small, right? And the complexity, I would say, comes in only in the delete function, which is more complicated. But even then, it's very close to what you would think of as the kind of the mathematical or the actual, like, here's really what it means to do a deletion, and then at the same time, it happens to actually implement it. And that's the more declarative nature of functional programming or Haskell. And I think you can see it quite well in this binary search tree example, where I'm just laying out the cases. I'm not having to deal with any other weird stuff like pointers or anything like that. I'm just laying out the basic crux of what the cases are. And it's quite easy actually to just read through it and even to check that it's correct. Okay, so we're out of time, and that's not bad because we only really have a little bit left to cover. So we'll do that on Thursday, talk about higher order functions. I'll stick around for a few minutes if people have any additional questions for me or about this stuff. This will all be in the lecture notes, so this is a good thing if you get stuck on the homework 10. This is great to kind of go back to, and maybe it'll help get you unstuck. It's got a lot of the pieces that we've been talking about so far. All right, have a great day, and I'll see everybody on Thursday.
Thanks, Professor.
Yeah, thank you.
Dr. Bowers, could you go
Yeah.
a little bit